Welcome to the MOOCs course Mechanical Unit Operations. The title of this particular lecture is Fluidization. So, till now what we have seen flow through single particles. When a single particle is settling, what is the settling velocity, etc. Similarly, for such kind of system is large number of particles are there, something like suspension. So, what is the hindered settling we have seen. We have also seen last two classes flow through packed beds, that is a column is there and then that column is packed with some kind of particles. Then the particle bed is constrained both at the bottom and then top, then the flow is taking place through bottom or the top. So, then what is the pressure drop? The pressure drop of that particular fluid flowing through a that kind of packed bed. So, those calculations we have already seen, we have also seen some kind of example problems, right. So, the pressure drop under such conditions like a flow through packed bed is nothing but a kind of total drag or the total resistance offered by the particles for a fluid to flow through such kind of packed beds. Now, this particular lecture what we do, we have a same kind of packing, we have a column, we have a kind of packing, but the packing is now is not constrained at the top, and then fluid is flowing through bottom to top in a upward flow direction. So, then what kind of flow characteristics will be there, how the packing structure will change. Obviously, the packing structure, whatever the packing is there, that is not constrained. So, because of the increased flow rate, there is a possibility that the packing structure will change. And then how this packing structure will change if the fluid is a kind of gas or if the fluid is a kind of liquid, that is gas solid system as well as the liquid solid system we are going to see. However, the packing structure that is going to be changing with respect to increased superficial velocity of the fluid, those characteristics are different for liquid solid system as well as the gas solid system. Despite of that one, if the velocity is sufficiently low enough, then both whether the gas solid system or liquid solid system, they will be behaving similarly. They will be behaving qualitatively similarly. So, that is the reason. Let us start with a kind of a general characteristics of a gas solid and then a liquid solid system and then go into the fluidization conditions. Let us say general characteristics of gas solid and then liquid solid system, and then under such conditions we take a downward flow through beds of particles. Okay. What we have a kind of column as I mentioned already, right. So, this column now is packed with some kind of particle packing material. So, we have different types of packing materials also, those things also we have seen. Now, let us say you take one type of particular packing material and then you pack it, okay, right. Now, you do a kind of downward flow here, okay. First, let us start with a kind of downward flow. So, now anyway at the bottom we should have a kind of perforated plate, okay. So, now in the downward flow what we do, we do not take any kind of constraint or confining the packing at the top. So, despite it is not confined at the top, the bed is not confined or not packed at the top, since the flow is coming downward, whatever the flow it is there, even if it is high flow rate is there, that is not going to change the packing structure, that is not going to change the packing structure substantially. So, which can alter the pressure drop. Since the packing structure is not changing, so then obviously the pressure drop is not going to change. So, whatever the pressure drop versus velocity or the flow rate relations are there for packed bed, those like Kozny-Karman equation or Blake-Plummer equation or Ergun equation, those we have derived, they will be valid here. So, why they are valid here? Because there is no relative motion between the particles here if the flow is downward, okay. So, there will not be any relative movement occurs between the particles except in the case of unstable initial packing. Of course, initial packing itself, if we have done loosely and there is a void space available, which can be by rearranging or some kind of fluid is coming at high velocity. So, such kind of small rearrangements will be there anyway. But if you take initial compact packing, so there will not be any kind of rearrangement of the packing if the flow is downward. If the flow is downward. So, under such conditions there will not be any relative movement between the particles. So, there will not be any kind of rearrangement of the packing. So, under such conditions whatever the Ergun equations are there, they are valid without any kind of difficulty, right. So, in laminar regions we have already seen from the Kozhnik-Orman equation, pressure drop is proportional to the superficial velocity V naught bar. Similarly, under the turbulent regions also we have seen that the pressure drop is proportional to the superficial velocity square, that is V naught bar square. So, that is coming out from this equation, Ergun equation that we have developed, which is having two contributions. The right hand side, the first term is a kind of viscous contributions or the contribution due to the laminar flow conditions, and then second term that is because of the turbulent or kinetic losses contributions, right. So, from the first part laminar conditions we can see that pressure drop is proportional to V naught bar, and then second case turbulent regions pressure drop is proportional to the V naught bar square. Okay. Now, let us say same packing, what we do, we take the same packing, we take a column, now we pack it with a certain kind of packed material, spherical particle or short cylinders or rashing ring or crushed glasses or whatever irregular particles you wanted to take, you take and then pack them. Now, here also we will not have any kind of constraint or the closing at the top, confining the bed at the top, that we are not going to have here also. But now here what we are doing in this case, we are taking the flow upward flow. We are taking the flow upward flow and then assume this column is sufficiently long enough, something like this. Okay, that is there is a kind of freeboard also. If it is a kind of, this area is a kind of packing area. So, this free space whatever is there, that is known as the freeboard. Okay. Okay. So, under such conditions whatever the upward flow through beds of particles, the frictional pressure drop, whatever the pressure drop that we have calculated through Ergun equation, that would be same here also as in the case of downward flow case, if the bed is constrained at the top. If the bed is constrained, so whatever the high velocity also you give, the particles are not able to escape from the packing area, because now the bed is completely packed, and the top also it is packed, though there is a free board area. So, if you constrain at the top, then also it will not, the packing structure is not going to change. The packing structure is not going to change. So, the pressure drop would be the same as in the case of whatever the pressure drop that you get in the case of downward flow through these beds of particles, or pressure drop should also be same as in the case of downward case if the flow is such that the structure of bed is not disturbed by the flow. If the flow is not such high, or the kinetic energy associated with the flow of the fluid is not so high that it is not going to disturb the packing structure, then also the pressure drop in the case of upward flow through beds of particle would be same as in the case of downward flow through the bed of the particle. So, under these two conditions it will be same, whether upward flow or downward flow, the pressure drop would be the same, right. But however, gradually increasing the flow rate, the point at which the drag on particles becomes equal to their buoyant weight, then what happens, bed rearrangement should occur within the bed, then expands in order to offer less resistance to flow. So, under such conditions what happens, the pressure drop is increasing, right, here is increasing with increasing the superficial velocity, whether upward flow or downward flow, as long as the packed bed conditions are prevailing, right. So, but what happens, if you do not have the constraint of the bed at the top and then you gradually increase the velocity, what happens, some kind of rearrangement of the particle packing structure takes place, and then bed starts expanding, and then pressure drop, what happens after that point, it will become almost like a kind of independent of the superficial velocity. Why? Because when these particles are moving away from each other, the packing is becoming looser and then bed is being expanded, the uh, the drag on particles whatever is there, that becomes equal to the buoyant weight of the bed. So, then what happens here, whatever the buoyant weight, that is gravity force due to the gravity minus force due to the buoyant is there, that should be balanced by the drag force, right. So, this divided by the, let us say you take the cross section area of the bed and then cross section area is S naught. So, then that should be equal to the drag force per unit area. So, that in the case of pressure drop, that in the case of packed bed, that drag whatever is there, that we are referring as a pressure drop, right. Pressure drop, or the resistance offered by the all the particle for this fluid to flow through this packing is that drag, the total resistance is represented by the pressure drop here. So, when the particles move away from each other, the packing becomes looser and then starts expanding. At that point, at the point where the expansion start takes place, the drag on particles becomes equal to their buoyant weight. So, that is under such conditions this would be happen, and then this is going to be constant after this point onwards. After this expansion taking place onwards, the drag whatever is there, that is going to be less, it is bed is going to offer less resistance to the fluid, because now particles are moving away from each other. So, the void space is increasing. So, initial whatever the linearly increasing or initial whatever the increasing pressure drop with increasing flow rate condition is there, that will come to the rest, and then from there that point onwards the pressure drop is going to remain kind of constant. Further increasing the flow rate, bed gradually become loose and reaches a point where the particles are separated from each other, and then particles become freely suspended in liquid stream, and then bed is said to be under fluidized conditions. The same thing we are going to see pictorially in the next slide anyway. By further increasing flow rate, particles move further apart, causing increase of bed voidage, but pressure drop remains approximately constant, that is, it is approximately equal to the buoyant weight per unit area of the bed, that is Fg minus Fb divided by cross section area, that should be equals to the pressure drop, right. The pressure, this is going to be constant, this constant pressure drop is going to be maintained from that point onwards, right. So, till this point the system behaves in a similar manner whether the fluid medium is gas or liquid. As I mentioned already, depending on the fluid medium that is being used to flow through this packed structure, whether it is a liquid or gas, the different characteristics may be obtained at higher velocities, especially at higher velocities. But till this point, the point where the fluidization takes place, or the point at which the buoyant weight of the bed is balanced by the overall resistance offered by the particles or the drag on all the particles, till that point the system is going to behave a quite similar way, whether the fluidizing medium is a kind of fluid or a kind of liquid, it does not matter. So, that is till the point where the fluidization starts, or till the point where the fixed bed conditions perishes, and then from there fluidization point starts, that breakthrough points, till that point fluid on the, whether the gas solid system or liquid solid system, it is going to behave similarly, right. So, after that, if you have a liquid solid system, liquid fluidized beds you are having, so the bed is going to expand in a more uniform way with the degree of agitation of particles increasing progressively. So, after this fluidization beginning or incipient point of fluidization, when you further increase the velocity, if the fluid is a kind of liquid, then a kind of a uniform expansion of the bed takes place, and then a kind of a constant bed density can be found at any location within the fluidized area within the bed. Okay. So, that is known as a kind of particulate fluidization or a smooth fluidization kind of thing. right. Pictorially we are going to see, but however after this point of the fluidation, or after this incipient point of the fluidation, if the fluid medium is a kind of gas, if the fluid medium is a kind of gas or gas fluidized beds if you are having, then that bed is going to behave very differently with increasing the velocity. It may have something kind of bubbling fluidation, it may have a kind of slugging fluidation, it may also have a kind of turbulent fluidation, etc. So, how they look like pictorially, that we are going to see here now. So, now see, the first case is a kind of case where we are taking the fluid medium, whether gas or liquid. So, now here what we are taking, with increasing velocity, the x direction increasing velocity, this is shown here, drawn here. So, what does it mean? What does it mean? So, velocity increasing. So, that means the first figure the velocity is low, but second figure the velocity is slightly higher than the first figure, and then third figure the velocity is further higher, and then fourth figure here the velocity is going to be highest amongst the all four cases. That is what mean by here this arrow increasing velocity. Okay. Now, the first picture what we have a kind of a packed bed. So, this is the kind of packed bed that we are having, or a kind of column is packed with some kind of a packing material, some kind of a packing material, and then at the bottom we have a kind of perforated plate here. We have a kind of perforated plate here. The perforation openings are smaller than the average size of the particles, so that the particle should not fall down through the perforation. And now we gradually giving a start allowing the fluid to flow upward here like this, right. So, as long as the velocity is low, the gas or liquid, whether you use gas or liquid to flow through this bed is not going to expand. It is not going to expand, or its packing structure is not going to change. If the packing structure is not going to change, the pressure drop versus the velocity or the flow rate relation whatever is there that we develop through Ergun's equation, that will be hold here also. And then these conditions we call it as a fixed bed. Remember here the top of the bed is not constrained, despite of that one the particles are not escaping from this area, the packing structure is not going to be disturbed because of this incoming the velocity flow rate, because incoming velocity or incoming flow rate of the fluid that is not having sufficiently large kinetic energy that it is going to disturb the packing structure. So, if the packing structure is not disturbed, so the behavior is going to be same as a kind of packed bed or fixed bed. Okay. Now, what we do? We increase the velocity slightly. Now, we increase the velocity slightly, so that what happens, particles move from each other, when the velocity is increased, the kinetic energy of the fluid medium that is sufficiently high enough that it is disturbing the packing structure. Now, that it is disturbing the packing structure, and now we can see the height of this bed is increased. Height of the bed initially it was up to this point, right. Now, it is expanded because now particles are moving from each other, and the packing is becoming loose, and then a kind of voidage is increasing here. And then why it is increasing gradually up to certain point where the drag, total drag whatever is there, or the total resistance is there, that is balanced by the buoyant weight of the bed. So, that is under this condition pressure drop is equals to Fg minus Fb divided by cross section area of the bed, right. So, until that point this is what the bed would be slightly like this. It will not be exactly kind of fixed bed, but the structure wise it looks like a uniformly packed structure, but uniformly expanded packing. Initially it was up to this location only, now it is slightly expanded, but it is still uniform. Okay. So, this condition is known as the minimum fluidation condition, or where the particles sufficiently apart from each other, and then at the point at which this buoyant weight of the bed is balanced by the total resistance offered by all the particles. Okay. So, this behavior also, whatever the minimum fluidation behavior that we are calling, that is going to be same whether the fluid medium is gas or liquid. Okay. Only the numbers will change, only the number will change depending on the liquid or gas, right, but the behavior would be the same, behavior would be same. Now, what does it mean by numbers will change? What is the minimum fluidation velocity at which the bed expand, start fluidizing, if you take the gas, if you take a liquid, keeping all other parameters same, like particle diameter, voidage, etc. So, then that minimum fluidation velocity may be slightly different, because the density of a gas and the density of a liquid that have been used, they will be different. So, that numbers would be different, but the flow patterns that you get, they will be like this only. Okay. Now, further you increase the flow rate, but you take now upward flow of the liquid. Now, we are taking only liquid. From this point onwards, we are separating liquid gas systems, right. So, further if you increase the velocity, increase the superficial velocity of the fluid, and then fluid, if it is liquid, then bed is going to be expand uniformly. What you can see here, whatever the expanded bed, that minimum fluidation condition is there, the same structure is there here also in the third picture also. Exactly the same structure is there, but the expansion is more, right. The uniform expansion is taking place, and then expansion is more, that is the difference only here. And then you can see here this at any location in the bed, you take the density of the bed, it is same actually. That means at any location within the bed, if you try to calculate what is the volume fraction of the solids and then what is the volume fraction of the liquid, it is not going to change much from one location to other location. That is the reason this fluidation is so smooth. Some books, this fluidation is also referred as a smooth fluidation, but particulate fluidation is more appropriate kind of terminology that you find in many books. This you will get in case of fluidizing medium is liquid at high velocities. High velocities, but it should not be very high. If it is very high, then particles may be rapidly moving away from each other, and then they may also come out of the column. Those section also we are having anyway, right. So, now at moderate to larger velocity, if the incoming fluid is a kind of gas, that is gas superficial velocity is moderate to large, that is sufficiently large or sufficiently away from the minimum fluidation velocity, then what we see, bed is behaving quite differently compared to the liquid solid system, or this is a kind of this we can say as a liquid solid fluidized bed, right, which is under a kind of pneumatic, which is under a kind of particulate fluidization condition. But now, if you have a kind of gas solid fluidized bed, and then the superficial velocity of the gas is sufficiently larger than the minimum fluidation velocity, we can have a kind of bubbling fluidization bed. That is what mean by we have some kind of voids or bubbles kind of things are forming here, like that I am arrowing like this, and then these voids or bubbles are almost free of the particle. Within these voids or bubbles, there are no particles in general, or very less particles in general, you can say. Such kind of voids or bubbles are formed. That is the reason these kind of behavior, if you find such fluidization of gas solid fluidized bed, is known as the bubbling fluidization. Some books you also find the terminology for this as aggregative fluidization, because earlier it was believed these particles are agglomerating and then forming a kind of clusters, agglomerates kind of thing, leaving more space for this gas to form a kind of voids or bubbles like that. But subsequently there were no reasons found that particles are being forming kind of aggregates. So, bubbling fluidization is a kind of more appropriate terminology here. Okay. Now, what we do, we take one more case, few more figures where we have a increasing velocity only. further increasing velocity, right. And then what we do, further increasing velocity, but the fluid whatever you take, that you take it now gas, and then the column diameter you make a smaller one, or you take a slightly narrower column, or compared to the these sections here, whatever the first 4 figures, the column diameter is sufficiently large compared to the fifth figure here, slugging fluidization. Here the column diameter is small. If you have a narrow column and then packing is there, and then velocity, the fluid medium that you are passing through this narrow packed column, if the fluid is a kind of gas, and then that superficial velocity of gas is very high, then most of the cross section of the column may be occupied by the slugs. The slugs are forming, like initially bubbles are formed. These bubbles are coming together and then forming kind of bigger slugs, and then these bigger slugs, they become so big that they are sometimes they almost occupy the entire cross section of the particles, so leaving only little space for the particles. They occupy entire cross section of the bed column, leaving only little space for the particles here, like this. Now you can see that is what mean by, so most of the column is occupied by bigger slugs. So that is the reason these these things are known as a kind of slugging fluidization, and then such kind of slugs whatever shown here, they are known as the axial slugs. Now if you take same narrow column, same packing, but the further you increase the superficial velocity of the gas, here also we are taking gas, in this case sixth figure, then also slugs will form, but the slugs are kind of flat, more or less kind of flat, having only a few particles occupied with this within the slug area. So this is also slugging fluidization, but these slugs are kind of flat slugs, because these slugs are having entirely occupying the cross section area of the column for some heights, like this, and they are more or less kind of flat. So that is the reason this fluidization is known as the slugging fluidization, but the slugs are flat slugs, right. Now further, if you increase the superficial velocity of the gas, we are still taking this gas solid fluidized beds. So further increasing the gas superficial velocity, the bubbles, whatever the voids or bubbles formed, and then particles will be at high velocity, a kind of turbulent conditions will prevail inside the bed, and then sometimes even the particles go out of the freeboard and go out of the column. So such particles are in general collected at the top by some means and then circulated back to the bed. So they are also known as the circulating fluidized bed. Okay. So circulating fluidized bed, that is known as this particle recirculation is there here. So like this. Okay. So these kind of beds, if you do not have a kind of recirculation of the particles, then we call them as a kind of turbulent fluidization. If you capture those particles and send them back as a kind of recycle to the bed again, so then you can call them as a kind of circulating fluidized beds. Okay. So now you can see here up to this point, first two figures, whether the fluidizing medium gas or liquid, the behavior is same, right. Then if you have a kind of liquid solid fluidized bed, then it will be like particulate fluidization kind of thing. But if you have a kind of solid gas solid fluidized bed, then the behavior may be quite different from the liquid solid particulate fluidization. You can see different types of behavior you can have if you are a fluid medium is a kind of gas, right. Then if you further increase the velocity to very large velocities, very high velocities, then particles are almost far away from each other, a kind of particulate conditions, particle transport kind of thing will take place because of the pneumatic conditions that are going to prevail because of the high velocities, and then such fluidized bed, or the fluidized bed under such conditions is known as the pneumatic transport or pneumatic fluidization. Okay. So, this kind of pneumatic fluidization may take place whether you have a gas or liquid fluidizing medium, but the velocity has to be very high. So, this is about the flow patterns of different types of gas solid as well as the liquid solid fluidization that we have. Now, what we do, the pressure drop versus the flow rate behavior we see for liquid solid systems. Okay, liquid solid systems. So, liquid solid fluidization, if we have the upward flow of a liquid through a bed of particles, then we can have the pressure drop versus flow rate or velocity on log curve. Then what we have a kind of representation like this. So, if the velocity is small, okay, initially velocity we are gradually increasing from no velocity or 0 velocity. So, if the velocity gradually increased like this, but the velocity is small, increasing, but velocity is small, then we can have a kind of increasing pressure drop with increasing velocity conditions up to point A, because up to this point the velocity is small, that it is not going to change the packing structure. So, since it is not going to change the packing structure, it is going to behave as a kind of fixed bed. The conditions, whatever the fixed bed conditions are there, they will be very much applicable, since for the fixed bed we already know that delta P by L is given by this equation, by Ergun's equation. From this equation we can say that the pressure drop increases with increasing the velocity. So, up to this point A like this. Now, but further if you increase the velocity, what will happen, a kind of bed expansion will take place. So, the slope will start diminishing and then maximum pressure will be attained at point B. Further, if you increase the velocity of the liquid, what will happen, particles move from each other, and then they will be under kind of expanded fluidized, but expanded fluidized conditions, like the particles are away from each other, and then the drag force is balanced by the buoyant weight of the bed until this point C, where the pressure drop slightly decreasing from point B. Okay, this decrement is usually very small, and then it is very difficult to trace out experimentally. Right. After reaching this point C, if you further increase the velocity gradually, what will happen? The pressure drop is going to be remain constant, because at this point C, the buoyant weight of the bed is balanced by the drag or the total resistance offered by the particles. So, the pressure drop is going to be remain constant from this point onwards. Right. So, after this A point, it is offering slightly less resistance, and then that less resistance is going to remain constant independent of the velocity from C point onwards. So, this is a kind of fluidized conditions, and then we are talking especially for liquid solid fluidization. So, it is we can say as a kind of particulate fluidization. Right. So, where the bed uniformly expands, and then bed density is going to be same at different locations within the column, wherever expanded column that you have taken, within the expanded bed wherever you take it. So, the pressure is going to be same. Okay. Now, if you wanted to decrease the velocity, now you have seen, you have gone up to the particulate fluidization conditions. Then what you are doing, you are decreasing the velocity, rather further increasing the velocity, so that the particles go out of the bed, and then the fluidization go into the pneumatic transport regime. So, let us not increase the velocity to such high velocity, because the particles are moving out, going out of the column. We wanted to stay within the column, because we wanted to track back the pressure drop versus velocity curve while decreasing the velocity. Right. So, when you attain the particulate fluidization conditions, and then you found that the pressure drop is independent of the velocity, then you are decreasing this velocity again here. So, gradually, so when you decrease it, so the CD curve now will be back to DC, and then from C it is not going to form taking this BA path, rather it will gradually further decrease up to point C. Why? Because now here initially we have the compact packing, with voidage epsilon. Now we have fluidized it, then we have fluidized it by increasing the velocity gradually, right. So, particulate fluidization situation has arrived. Now we are decreasing the velocity, so the particles are settling down. And there will be a point, all the particles are touching to each other, and then further decreasing the velocity, the particle rearrangement is not going to be so high that the compact packing you will be getting as it was kind of initial packing. You are not going to get compact packing as initial packing, right, because the bed has disturbed. Initial compact packing we do usually by vibrating, shaking, etc., right. So, once this point E has reached, then it is particles almost like resting onto each other, not only just touching, they are resting onto each other. It's a kind of bed has formed by particles resting onto each other kind of thing, and then further decreasing the velocity, they are not going to rest or compress, the bed is not going to compress again, right. So, but again the particles are resting onto each other, what happening, it is having a kind of a fixed bed condition has arrived. But the packing is not as compact as initial compact. So, the voidage is more, the bed expands slightly expanded and voidage is more, right. If the bed is expanded slightly, so the voidage is more. So, obviously, if the voidage is more, the pressure drop is going to be less. That is the reason from this E point onwards also, when you decrease the flow rate or velocity, the pressure drop is decreasing with the velocity, but it is not following initial OA curve, but it is following this EF curve like this, because now the bed because of the fluidization it has taken place, and then by decreasing the velocity, particles are settling and touching each other and then resting onto each other, but that resting onto each other is not providing the initial compact packing kind of thing. So, but it is having slightly different voidage, that is slightly higher voidage, or we can say this is the maximum voidage possible under fixed bed conditions. Under fixed bed conditions, whatever the voidage, higher voidage is there at point E, that is the maximum voidage possible under fixed bed conditions, or the minimum voidage that is possible under the fluidized bed condition. So, because after that one, if you increase the fluid velocity, the voidage is going to increase, right. So, that is the reason this point, the point E is known as the point of fluidization or incipient point of fluidization, and then corresponding velocity we know we call it as a kind of minimum fluidization velocity, and then that maximum voidage is known as the voidage at the minimum fluidization conditions epsilon m. So, remember epsilon m is a kind of maximum voidage possible under the packed bed conditions, and then it is minimum voidage possible under the fluidized bed conditions, and this is the point that occurs at this velocity Vm, that is the minimum fluidization velocity. So, below this minimum fluidization velocity, bed behaves as a kind of a fixed bed or packed bed, and then beyond this minimum fluidization velocity, the fluidization will take place, and then bed behaves as a kind of a fluidized bed, right. So, now initially you increase the velocity, you decrease it. So, then while increasing the velocity 0, A, B, C, D curve you found for this pressure drop versus flow rate, but when you decrease the velocity, you found this curve D, C, E, F like that, they are not matching, only C, D line is same while decreasing or increasing the velocity. Okay. So, this increasing velocity curves are the solid line curves, decreasing velocity curves are a kind of dotted line curves here. Okay. But now again, if you after decreasing it, again if you increase it, will it follow that OA curve or FE curve? So, the packing is not as kind of initial compact packing, it is going to follow this FE curve, then E to C, then C to D curve. This curve only it is going to follow. It is not going to trace back to 0 A, B, C curve at any conditions once it has been fluidized, or once the initial compact packing has been disturbed, we will not be able to trace back this O, A, B, C for any flow conditions. Okay. So, now the same thing we can see for the case of bed height also. Bed height versus superficial velocity if you see. So, this bed initially what happens, initial compact height, whatever bed height was there, initial compact packed bed height or initial packing height, whatever compact packing you have taken, that it will be there up to certain velocity, it will not be disturbed, but after certain velocity what will happen, this will take this curve path like this, because this is the reason where the expansion of bed is taking place, and then buoyant weight of the bed is balanced by the overall resistance offered by all the particles, and then after this point, if you further increase the velocity, the bed height is going to increase like this. Okay. Now, your fluidized it sufficiently, you can see the fluidized conditions, okay, a proper fluidized condition, not just expanded or minimum fluidized conditions. After reaching that sufficiently high fluidized condition, you are decreasing the velocity. When you decrease the velocity, you can see that bed height gradually decreases with the decreasing superficial velocity, but after this point it is not going to come back like this, the previous curve, but it is going to be constant like this, because at this by the time velocity decreases to at this point, the particles are settled and they are resting onto each other, and then further compact packing of those particles is not going to take place. So, that packing height is slightly higher than the initial packing height. So, while decreasing the velocity, the height would be slightly higher, and then because of this slightly higher packing height, the voidage is going to be higher. So, the pressure drop is going to be lower, as we have seen in the previous curve. So, if you wanted to find out this superficial velocity from bed height versus superficial velocity curve, the velocity corresponding to this point is known as the minimum superficial velocity. Okay. So, this is about the liquid solid fluidization. Now, we are going to do the minimum fluidization velocity calculations, and then we have seen this minimum fluidization part up to the minimum fluidization conditions, whether it is a gas or liquid fluid medium that we are using, the behavior is going to same. So, the analysis equation development is going to be same for gas solid or liquid solid fluidized beds. Okay. So, whatever I explained in these figures have been given as a kind of notes here for the convenience of the students, right. So, now we see some experimental results, pressure drop versus the flow rate for a CMC solution flowing through a column having 100 mm diameter with packing 3.57 mm glass piers. So, they have a kind of 100 mm column. In this column, at the bottom there is a perforated plate, and then these glass piers are packed to certain initial height like this. Okay. Compact packing was done using this glass particles 3.57 mm, right, and then through the bottom they allowed CMC solution to flow through up, and then experimentally what is the delta P versus V naught bar or superficial velocity is there. So, that captured experimentally they have calculated and then put in pictorially like this. So, now we can see to certain velocity these points are experimental points, actually all these things are experimental points. So, they are slightly scattered, but if you draw a kind of curve fitting line, so up to certain velocity it is gradually increasing, and then there is a diminishing of slope, and then pressure drop slightly increasing up to point C, and then after this pressure drop is almost remaining kind of a same constant. So, the point here up to this whatever is there, that point, the velocity corresponding to this point where from where the pressure drop is becoming constant onwards, that velocity is known as the minimum fluidation velocity. Below the minimum fluidation velocity, bed behaves as a fixed bed where the pressure drop increases with the flow rate. After the or beyond the minimum fluidation velocity, the bed behaves as a fluidized bed where the pressure drop remains constant, or pressure drop remains independent of the superficial velocity of the fluid. Okay. So, velocity corresponding to the incipient fluidizing point can be calculated by equating the pressure drop across the beds to its buoyant weight per unit area, and then voidage at the onset of the fluidation or incipient point of the fluidation should correspond to the maximum value attainable in the fixed bed conditions. Okay, in the fixed bed conditions. Therefore, in the fluidized bed, the total frictional force on the particles must be equal to the buoyant weight of the bed. When you do these things, you will get this expression. We are going to derive this one anyway. This is coming simply by minus delta P is equals to Fg minus Fb buoyant force divided by cross section area. You substitute this buoyant force and gravity force, simplify, then you will get it. So, in Ergun's equation, in place of delta P, simply you write this equation. So, that equation, whatever the simplified equation is there, that will be valid for the fluidized bed conditions. Okay. So, minimum fluidation velocity of gas solid and liquid solid fluidation. Remember, up to the fluidation incipient fluidation or the minimum fluidation conditions, whether the fluidizing medium is a gas or liquid, it is going to behave a kind of a similar way. So, whatever the minimum fluidation velocity calculations are there, they are going to be same whether the fluidizing medium is a gas or liquid. Okay. So, pressure drop across the bed should be equated to the gravitational force minus buoyant force per unit cross section area. So, this is the gravity force, this is the buoyant force divided by the cross section area S naught. So, from these two terms, mg by rho p, if you take common, mg by rho p multiplied by rho p minus rho by S naught. Now, m by rho p is what? M by rho p is nothing but the volume of the particles within the bed, volume of the particles, all the particles within the bed. Okay. So, that you can calculate by L S naught multiplied by 1 minus epsilon, because this is the bed, initial bed that you are having. So, let us say all this is kind of packed conditions. So, if this is the initial packing height L and the cross section area of this bed is S naught. Okay. So, what is the volume, total volume of the bed? Bed volume is going to be L multiplied by S naught. This bed is consist of particles and then void spaces, right. So, then volume of particles, all the particles would be what? L S naught multiplied by 1 minus epsilon, where epsilon is the void space or the volume fraction of the void space is epsilon. So, 1 minus epsilon is the volume fraction of the particles within the bed. So, volume fraction of the particles multiplied by the volume of the bed, if you do, you get volume of the particles, within the bed. So, that we are substituting L S naught multiplied by 1 minus epsilon, this S naught is cancelled out, L you can take to the left hand side. So, you have delta P by L is equals to 1 minus epsilon G delta rho, right. So, now this equation we are going to use in Ergun's equation in order to find out minimum fluidation velocity, or the point at which, or the velocity when you are gradually increasing, there would be a certain velocity at which the pressure drop would be equal to this one, and after that it is going to be constant. So, corresponding velocity we can call it as a minimum fluidation velocity V O m bar, and then corresponding voidage we can call it epsilon m. Okay. So, at this minimum fluidation condition, so wherever the minimum fluidation conditions appeared, so the delta P by L is going to be 1 minus epsilon G delta rho P. Okay. So, that is known as the minimum fluidation condition, or the velocity at which delta P by L is going to be equal to 1 minus epsilon multiplied by G delta rho as just derived. So, that is the minimum fluidation point, and then that minimum fluidation condition, the voidage is going to be maximum attainable voidage under packed bed condition. So, that we are writing epsilon m, right. Initial packing is epsilon, but the initial voidage of the bed is epsilon. Initial compact packing, when you do, the voidage is whatever the void volume fraction is there, that is epsilon, but after fluidation has taken place, so particles are loosely packed and started expanding, where the pressure drop is balanced by the buoyant weight of the bed. The fluidation is increased slightly, and then that is the maximum voidage attainable under the packed conditions. So, that we are writing epsilon m, and then velocity is minimum fluidation velocity, where V naught bar we are replacing by V naught bar m, right, or V naught m bar. So, this these two we replace in the Ergun's equation. Epsilon we replace by epsilon m, and then V naught bar we replace by V naught m bar, and then in the Ergun's equation delta P by L we replace by 1 minus epsilon G delta rho. So, this is nothing but delta P by L of our Ergun's equation, right, and then this is the right hand side term as it is, but what only thing that we have done here is velocity, superficial velocity we replaced by the minimum fluidation velocity, and then voidage we replaced by the maximum voidage at minimum fluidation conditions. So, this is the minimum voidage under the fluidized conditions, but maximum voidage under fixed bed conditions, or the trade off point from where the fixed bed is going to become fluidized bed, that point velocity voidage is the maximum for the packed bed conditions and minimum for the fixed fluidized bed conditions, minimum for the fluidized bed condition, maximum for the packed bed conditions. So, that epsilon m we replaced. So, in the Ergun's equation delta P by L we replaced by G multiplied by 1 minus epsilon m multiplied by rho P minus rho as just we derived, and then in the right hand side everywhere velocity we replaced by the minimum fluidation velocity, and then epsilon we replaced by epsilon m. Okay. That is the only change we have done. So, this equation one can solve to get the minimum fluidation equation. It is a kind of quadratic equation that you get when you substitute all the properties like voidage, gravity, densities, and then packing size, etc., shape factor, etc., all those things when you substitute, you will be having a quadratic equation for a minimum fluidation velocity that you solve, then you get the minimum fluidation velocity. We are going to do one example problem also. So, this now what we do from this equation, this 1 minus epsilon m, if you cancel out the other side from both the sides, so then you have this further simplified equation. Okay. From here also you can get the minimum fluidation velocity. Indeed, both of them are same actually, they are not different. So, now in the case of single particle conditions, a single particle settling in a column of fluid, if we know the Reynolds number, so then we have a kind of a expression for a free settling velocity of the that particular particle. If we know that the particle settling under the Stokes regime, then we have a kind of a free settling velocity for that particle under Stokes regime. Similarly, if we know that particle is settling under the Newton's flow regime, then we have a kind of separate settling velocity equation under the Newton's flow regime. So, we try to do similar kind of thing. If we have a kind of flow conditions, laminar flow conditions, small Reynolds number conditions, where only viscous losses are contributing more, and then kinetic losses are negligible or very small compared to the viscous losses, then we can develop an expression for a kind of a minimum fluidation velocity. Similarly, we can do if the flow is very high and then viscous losses are going to be very small, then compared to the kinetic losses. So, then considering only kinetic losses part, we are going to develop another equation for the minimum fluidation velocity valid for high Reynolds number flows. So, for REP less than 1, so the equation number 2, the previous equation, left hand side is as it is, right hand side we are taking only first term which is contributing to the viscous losses, because whatever the kinetic losses terms are there, second term 1.75 etc., that is very small, 0, very small, that it can be neglected compared to the viscous losses. So, we take only first term in the left hand side. It is exactly the similar way what we have done for the packed bed conditions when we are deriving magnitudes of viscous losses and kinetic losses etc. So, we take only viscous losses for small Reynolds number because they are dominating one. So, that means in the right hand side we have to take only first term, and then you simplify it, then you will get a kind of expression for the minimum fluidation velocity as given by this equation number 3. Remember, this equation is valid only if the Reynolds number is small or REP less than 1. Empirical relations based on experimental studies indicated that this VOM bar, what we are seeing here, it is proportional to dP square. From theoretically what you find, minimum fluidation is proportional to dP square, but experimentally it is found that VOM bar or the minimum fluidation is proportional to the dP to the power of slightly less than 2, not proportional to 2, but slightly less than 2. That is, some deviations from the experiments are in general possible. So, those deviations are, this is one deviation, and another deviation what we see here from this equation number 3, that minimum fluidation velocity is inversely proportional to the viscosity of the fluid under the small Reynolds number conditions, but experimentally it has been found that it is not quite inversely proportional to viscosity. It is not quite inversely proportional to viscosity. Okay. So, some discrepancies between the observed and calculated minimum fluidation velocities are in general possible. Some of the discrepancies we have seen that they are not quite proportional to the minimum fluidation velocity is not quite proportional to the dP square. It is proportional to dP power slightly less than 2, and then it is not quite inversely proportional to viscosity experimentally, but theoretically it has been found that minimum fluidation velocity is inversely proportional to the viscosity of the fluid. Such kind of discrepancies may be there. They are in general attributable to something like channeling may occur during the fluidation conditions. There may be some kind of wall effects, there may be some kind of agglomeration of particles also, depending on the size of the particles. Some particles may be agglomerating, then also it may be possible. Sometimes if you have a kind of needle like kind of particle, so then interlocking of particles may also take place. So, then again under such conditions fluidation behavior may be slightly different than observed ones. So, because of these reasons there may be some kind of discrepancies. Now, what we do, we try to see the free settling velocity of a single particle and then compare with a kind of a minimum fluidation velocity for small Reynolds number conditions. So, small Reynolds number conditions when REP is less than 1, we have already seen for spherical particle free settling velocity is nothing but g dP square delta rho by 18 mu, right. So, now this equation, what we do, we take the ratio between this terminal velocity and minimum fluidation velocity, that is ut by V naught O m bar. So, this equation divided by equation number, this one divided by equation number 3, that just previously derived equation if you do. So, ut by V O m bar. So, this is ut free settling velocity of single particle, and then divided by V O m bar is nothing but g delta rho pi s square dP square epsilon cube by 150 mu 1 minus epsilon, right. So, 1 minus epsilon m actually, right. So, now here g you can cancel out, dP square you can cancel out, and then let us say we are taking spherical particles, so let us not worry about the shape factor. So, mu and then mu is also cancelled out, and then delta rho is can be cancelled out. So, what we are having? We are having 1 minus epsilon m by 1 minus epsilon m cube, 1 minus epsilon by epsilon m cube multiplied by this 150 by 18, that is 8.33. That is what we get here. So, now in general if the packing is done by the spherical particles, so then voidage is in general 0.45, or the voidage at minimum fluidization condition is approximately 0.45 if you do the packing using spherical particles. So, under such conditions, if you take epsilon m is equals to approximately 0.45 and then substitute in previous equation, the previous equation is this equation. In this equation, if you substitute epsilon m is equals to 0.45, which is mostly accepted value for packing with spherical particle, then you can get this ratio as kind of 50. That means free settling velocity is almost 50 times the minimum fluidization velocity. So, if your the velocity whatever you are going to provide for minimum fluidization to take place, at least minimum fluidization to take place. So, it has to be at least 50 times the free settling velocity of the single particle. You find out what is the free settling velocity of single particle ut, and then you multiply by 50, whatever the value that you get, that much velocity, minimum velocity you should provide, so that to have a kind of minimum fluidized conditions or fluidization with a few particle going out. So, that is the reason we evaluated this kind of ratio. That is the reason we evaluated this kind of ratio. Okay. So, now that is a bed that fluidizes at 10 mm per second could probably be operated with velocities up to 50 times higher, that is 500 mm per second, 0.5 meter per second, with few particles carried out with exit gas. Okay. For mixture of particles different diameter, these causes more carryover or entrainment of fines than of average size particles in general, but most of fines can be recovered by filters or cyclone separators and returned to the bed. If you have a single shape particles, that is fine, but if you have the different types of particle mixture, then it is possible that some particles having smaller size, and then depending on their shapes they may be easily carried over under these kind of velocities whatever you are operating based on the spherical particle calculations, right. So, but however they can be collected and then circulated back to the bed. So, some fluidized beds are operated at velocities of 100 times minimum fluidization velocity with high entrainment, but nearly complete recovery of the entrained solids. Sometimes if you are not worried about the entrainment of the solids, because you are sufficiently able to recover them and then send back to the bed, so that you can have a circulating fluidized bed. So, under such conditions some fluidized beds are even operated at 100 times the minimum fluidization velocity, provided the flow is under the laminar flow conditions. This is all, remember, we are doing under the laminar flow conditions. Okay. Once develop the equations, minimum fluidization equation, generalized equation, after that this discussion we are doing for a small Reynolds number. We are going to do for high Reynolds number cases also, where you don't need to give such high number of times the minimum fluidization velocity in general. Okay. That we are going to see anyway. For non-spherical particles, whatever the equation 4 that we developed indicated a wider range of fluidization without any entrainment. However, the value of epsilon m is generally greater for irregular particles than for spheres. These are all, these observation 2 points are in general by the experimental observations. So, for instance, if you have a non-spherical particle with a shape factor 0.8 and then minimum voidage at the minimum fluidization conditions epsilon m, then ut by VO m bar you are going to be 52, slightly more than the spherical particle kind of case, where we are by using just epsilon m 0.45, if you use the spherical particles, this ratio we got it as 50, but now here if the irregular particles you use and then slightly more wattage you use, then also it is coming out to be 52, slightly higher than the spherical particle conditions. So, now we take for high Reynolds number conditions. Okay. High Reynolds number conditions, the kinetic losses are important. So, right hand side of the Ergun equation we are taking only the second term, and then left hand side term delta p we are replacing by g delta rho by left hand side delta p by L we are replacing by g delta rho multiplied by 1 minus epsilon m. So, there seems to be 1 minus epsilon m in the right hand side also, that epsilon m 1 minus epsilon m left hand side and right hand side is cancelled out, or whatever the equation 2 that we derived, left hand side we are keeping as it is, right hand side we are taking the term associated with the large Reynolds number, that is the second term only we are taking. This is valid for large Reynolds number 10 power 3 or more. So, from here what you get, minimum fluidation velocity is nothing but square root of g delta rho pi s dp epsilon m cube by 1.75 rho. This is what we are going to get. Now, here also what we do, we take a free settling velocity of single particle, but under high Reynolds number conditions, that is Newton's flow regime, we know the settling velocity of the single particles, Newton's flow regime, we know this is Newton's regime, that is REP is greater than 10 power 3, then for single particle free settling velocity we got it like this. Now, here also we take the ratio between the free settling velocity and minimum fluidation velocity under high Reynolds number flow conditions, then we have this one here. Okay. So, both the powers are 1 by 2. So, here g dp, here g dp can be cancelled out, here rho can be cancelled out, here delta rho p, delta rho, here delta rho can be cancelled out. So, what we have 1.75 multiplied by square root of 1.75 divided by epsilon m cube. So, that is coming out to be ut by VO m bar is approximately 2.32 divided by epsilon m power 3 by 2. Now, let us say spherical particles with epsilon m is equals to 0.45 as we have taken previously. So, if you substitute here, then you can see this ratio ut by VO m bar is just 7.7, it is not 50 or 52 as previously we have seen. Okay. Just you can see, that is the reason I am saying, I was mentioning, depending on the flow condition, whether the laminar flow conditions you want to have or the turbulent flow conditions you want to have, accordingly the free minimum fluidation velocity you have to find out, and then accordingly those number of times you have to multiply, so that to have a proper fluidation. Okay. So, these previous two expressions for low Reynolds number and high Reynolds number we have seen. So, if you do not know flow regime, if you wanted to know flow regime, you should know REP, that is dp rho VO m bar by mu 1 minus epsilon m, that you know. So, that is velocity you should know, then only you know the Reynolds number, then only you can use those minimum fluidation velocity conditions. Indeed, those simplification we have done in order to get the minimum fluidation conditions, minimum fluidation velocity. So, that means you cannot know the Reynolds number, so you cannot use the equation number 3 and 4 which we just derived. So, in order to overcome such kind of problems, what we do, we use equation number 2. Equation number 2 whatever is there, when you substitute the particle characteristics and then fluid physical properties, rho, mu, etc., voidage, etc., if you substitute, you will get a kind of a quadratic equation for minimum fluidation velocity that you can solve to get the minimum fluidation velocity. But alternatively, there is another method, where this is the equation number 2 we are having. This equation, both sides what you do, you multiply by rho dp cube by mu square multiplied by epsilon m cube by 1 minus epsilon whole square. This particular term you multiply both sides for this equation number 2. When you do these things, you get this one. What we have done here, nothing but you just multiplied by this term here, and then in the right hand side also both the terms. Then what happens, that again I have written the same equation here. So, now you can see in the left hand side I am not going to do anything, right hand side what we can do here. So, this square of the viscosity and then this viscosity term is gone cancelled out, we can cancel out, and then this 1 minus epsilon m and then the square of 1 minus epsilon m is cancelled out, epsilon m cube and then epsilon m cube is cancelled out, and then this dp square is cancelled out with the cube of the dp. So, there is 1 dp, right. So, then what we have here, rho dp vo m bar divided by mu and then divided by 1 minus epsilon m. So, that is nothing but Reynolds number. Forget about this pi s square. So, we take for the spherical cases as of now. Similarly, here also this dp here and then cube of the dp if you take. So, you have the dp square here and then vo m bar square is already there. This epsilon m cube, this epsilon m cube you can cancel out, mu square is there, 1 minus epsilon m whole square is as it is. This rho multiplied by rho, what we can have, rho square. So, here rho dp vo m by mu 1 minus epsilon whole square, you can write it out. So, that means nothing but that is the Reynolds number. So, left hand side is as it is, right hand side 150 by pi r square multiplied by this term is remaining plus 1.75 by pi s multiplied by this term is remaining, and this is nothing but our REM or. So, this is nothing but Reynolds number definition, but Reynolds number for packed bed we have defined it as rho V naught bar dp by mu into 1 minus epsilon. This is how we define the Reynolds number for packed bed. So, since we are doing this is at the minimum fluidization condition, this epsilon should be replaced by epsilon m and then VO bar should be replaced by minimum fluidization velocity. So, that is the reason REM I am calling it, or the Reynolds number at minimum fluidization conditions. Okay. So, left hand side is equals to 150 REM plus 1.75 REM square for spherical particles, that is what we get here. So, left hand side whatever is there, this term in general is known as the Galileo number for spherical particles, right. So, this pi s we have taken because now we wanted to do it for spherical particle conditions. So, then left hand side whatever this term is there, that is known as the Galileo number. So, this is just a kind of, in order to avoid the calculation of VOM and then finding out the Reynolds number, and from the Reynolds number we can find out the minimum fluidization velocity. This is just an alternative approach, but this approach is having no advantage. It is similar to whatever the k factor that we have developed for a case of single particle. For a case of single particles, what we have? We have this k. K is nothing but dp cube root of g rho delta rho by mu square. This is what we have k for single particle. Or if k is less than 2.6, we know this is a Stokes regime. If k is greater than 68.9, we know it as a kind of Newton's flow regime. In between it is intermediate region. So, then calculation has to be done. So, that advantage was there by here by finding out this k factor, right, in this case of single particle case. But here in the case of packed bed, the fluidized bed, that advantage is not there, because in the case of packed or fluidized bed we do not know exact transition of from laminar to turbulent conditions, right. Like REP if less than 1, then we say that it is Stokes flow regime for a single particle condition. If REP is greater than 10 power 3, then we can say it is a kind of Newton's flow regime. So, accordingly we do calculation. So, this is the advantage of having this k factor or k parameter which is independent of velocity. It was useful in calculating out the free settling velocity. Similar analysis we have done here. People say this is a kind of Galileo number. We can say it is a kind of k cube only. It is just this term in the Galileo number, or you can see here also in the Galileo number whatever this term is there, the first two term, this term, this exactly is nothing but your k cube. So, probably if you multiply this one, so then it may be k cube factor or cube root of this one is going to be k for a kind of packed or fluidized bed conditions. But there is no advantage of doing such kind of analysis here, because packed bed or fluidized bed we do not know, there is no clear transition between laminar to turbulent flow condition. So, there is no point of using it. So, even if you have written this equation in terms of Galileo and Reynolds number like this, the calculation is again going to be trial and error kind of thing, or solving this equation for Reynolds number, and from that Reynolds number you are going to find out the minimum fluidation velocity. Rather doing that one directly, you can calculate equation number 2 you can use, and then obtain quadratic equation which you can solve to get the minimum fluidation velocity. The references for this lecture are unit operations of chemical engineering by McCabe, Smith and Harriet, unit operations of particulate solids theory and practice by Ortega-Revas, and then Carlson and Richardson's chemical engineering series 2nd volume by Richardson and Harker, transport processes in and unit operations by C.J. Giancopoulos, and then unit operations by Brown et al., and then introduction to chemical engineering by Badger and Banchero. But however, most of this lecture is taken obtained from these two reference, that is McCabe, Smith and then Harriet, and then Richardson and Harker. These two books are referred to prepare today's lecture slides. Thank you.